So the idea of magnetic flux, if you've got some loop of wire and some magnetic field, let's say a magnetic field pointing straight up. And we've got a loop of wire shaped like this. Does that make sense in terms of 3-dimension? Like you've got this wire going sort of in this shape. So like actual physical loop of wire held up sort of diagonally like this. And in that case, the magnetic flux, if we got a magnetic field and this loop of wire, how do we define flux in the first place? Flux actually mean? Either conceptually or as an equation. When we talk about magnetic flux, what does it mean?
Casey, this is what does the green part say when it says up, like the arrow pointing or the magnetic field?
Yeah. So the B vector, the magnetic field.
Oh, okay.
So that's the magnetic field vector. We're just assuming is straight up and uniform, same everywhere. And then we've got this loop of wire in the presence of the magnetic field. Is this wire experiencing flux? Is this loop experiencing magnetic flux? Yeah, certainly looks like it's got flux in the sense that these field lines, these vectors are passing through the loop. In general, if you've got field lines going through the interior of the loop, that counts as flux. So the flux is just the extent to which the field lines or field vectors are passing through the interior of the loop. So for instance, if this is our loop of wire, let's say we've got a magnetic field pointing straight up. So this pencil is magnetic field vector. If we've got a loop of wire like this, the magnetic field vector is passing through the interior. So that counts as flux. On the other hand, if we hold the loop like this and have the magnetic field going like this, if it's just skimming along the surface, it's not really going through the loop. So this would count as zero flux. If it's going through like this is going through a large amount. So that would be a lot of flux. If it's on some diagonal, that's passing through a little bit, but not as much. So that would be a smaller amount of flux. And if it's just skimming along the surface, that's no flux at all. So that's what flux means conceptually. To what extent is the magnetic field passing through the interior of the loop? We can also define it mathematically based on what quantitative properties, what things we could actually measure numerically determine how much the field lines are passing through the loop. That is, what is it about this loop or this magnetic field or how they're related to each other that determines how much the field lines are passing through the loop? Yeah, the area, so the surface enclosed inside that loop makes a difference. If we made the area larger, let's say exact same location for the loop, exact same magnetic field, but we just looked at a larger loop, that larger loop is going to be enclosing more magnetic field lines. Or alternatively, if we make the loop smaller, it's going to be enclosing fewer magnetic field lines. So the surface area enclosed inside the loop makes a difference here. More area means more flux. So the flux should be proportional to area. What else do you think would make a difference here? Let's assume the area is constant. You're just taking this single loop and holding it in place. How else could you increase or decrease the number of field lines that pass through that? Yeah, the strength of the magnetic field. And visually, we represent a stronger magnetic field with more densely packed arrows, more arrows per centimeter or per square centimeter, I guess. So if the magnetic field is stronger, you have more densely packed arrows. And so that's going to mean more arrows going through the interior of the loop. And of course, there was presumably going to be arrows outside the loop as well. But for flux, we only care about the arrows passing through the interior. And the stronger the magnetic field is, the more field lines there are per square centimeter, the more densely packed they are. So that's also going to be more field lines. But also the direction is going to matter as well. If we have this loop, let's say we've got this exact same loop, but we tilt it like this. In that case, the field lines aren't really going through it, they're just skimming along the surface. Whereas if we tilt it like this, they're going to be going through it much more strongly. So the angle at which the loop sits is going to make a difference as well. And so how do we represent that in the equation? How would we describe how the angle makes a difference here? The orientation of the loop. Yeah, this is where we get a cosine theta in the equation. And what that actually means, the theta in this equation, it's tempting to think of that as the angle between the surface and the magnetic field. But the problem is, it is mathematically very inconvenient to try and measure an angle between a surface, like a plane, and a vector. Like, would you measure this angle, or would you measure this angle, or this angle, or this angle? There's infinitely many different directions you can measure the angle from. So instead of trying to define an angle between a surface and a magnetic field, we're going to do the same thing we did for refraction. We're going to draw in a normal vector. So on the surface itself, usually in the middle, but it doesn't really matter where, you draw in the normal vector. The normal vector is perpendicular to the surface itself. So this was the normal vector, usually written as n, usually n hat. This hat sign here, this means this is a vector, but its length is exactly 1 unit. So this is just an arbitrary length 1 vector in a direction perpendicular to the surface. Mathematically, it's fairly straightforward to create a vector that's perpendicular to a surface, and it's very straightforward to measure the angle between vectors. So if we consider the normal vector and the magnetic field within that region, we can define the angle between those. So that's the theta we're talking about. In this context, theta means the angle between the normal vector and the magnetic field. So that's the theta here. Between the magnetic field vector and the normal vector perpendicular to the surface. Any questions on the geometry of that so far? So if we look at a couple of the extremes here, let's say you've got an upwards magnetic field and we want the most flux. So if you could rotate this loop however you want, how would you arrange this loop to get the most flux, the most field lines passing through it? Like, how should I hold this in order to get the most field lines passing through it? Yeah, if I just hold this flat horizontally, I'm going to get the most field lines passing through. So let me draw that out. If the loop of wire is perfectly horizontal, and this is specifically with the magnetic field lines upwards as shown here, this is going to lead to a large amount of flux. And it's tempting to call this magnetic field perpendicular to the surface, which it is. But that's not the angle we're talking about in the equation. The angle we're talking about is the angle that the normal vector makes with the magnetic field. So n hat, the normal vector, in this case would be straight up. Or alternatively, we could draw the normal vector straight down. In both those cases, though, if we draw a normal vector straight up, what's the angle between the normal vector and the magnetic field? If the normal vector is straight up and the magnetic field is also straight up, what's the angle between those? Yeah, that's going to be 0. So theta would be 0. And what's the cosine of 0?
One.
Yeah, cosine of 0 is 1, which is the largest cosine can possibly be. So if the surface is oriented perpendicular to the magnetic field, that means the angle is 0 because the normal vector is in the same direction as the magnetic field. That leads to cosine of 0, which is 1, so flux is just A times B. That's the largest it can possibly be. Alternatively, if we draw the normal vector straight down, what's the angle between an upwards magnetic field and a downwards normal vector?
180.
Yeah, theta would be 180 degrees. And what's cosine of 180 degrees? Yeah, that's going to be -1. So same absolute value, just a different sign. And this can be kind of problematic. If you had the option of choosing 2 different normal vectors, because there's 2 directions that are perpendicular to the surface, you could choose either one. The math is going to ultimately work out the same way in terms of the final result. But choosing a normal vector opposite to the direction of the magnetic field leads to a negative amount of flux. Again, is still going to lead to the same result in the end. But those extra negatives, which will cancel out eventually, make things confusing in the in-between steps. So I would recommend, since you've already got a choice of 2 possible normal vectors, just choose the one that most closely agrees with the existing magnetic field. That'll ensure that the flux is positive, which again doesn't influence the final result, but it makes it easier to understand what's going on in the in-between steps. So when you've got the choice, choose the normal vector that's already in the same direction as the existing magnetic field, or at least close to it. Like in this case, we could choose a normal vector up and to the left or down and to the right. But up and to the left is most closely agreeing with the existing magnetic field. So that's going to lead to a positive value for flux and make the numbers easier to visualize. Any questions on that so far? On the other hand, what if we have, let's say, again, we have an upwards magnetic field. But we take that loop and rotate it so it's oriented vertically. Why it doesn't affect the final result? It's specifically not going to affect the current, because when you change the flux, you end up with induced current. That's what this is ultimately building up to. When you, like, let's say you move the loop around. The laws of physics don't care which way we say it is positive. We could say this is the normal vector. We could say this is the normal vector. The direction we choose for the normal vector is really just a matter of notation. It's a matter of what coordinate system we're choosing to use. But the physical reality doesn't care what we're calling up or what we're calling down. The physical reality just cares about what's actually physically happening. The normal vector is just a placeholder we're using to describe the results mathematically. But if you choose the opposite direction for normal vector, you do get a negative here, but you end up with another negative in a later step of the calculation that cancels it out anyway. So the result is going to be the same. It's just that it's more difficult to visualize because you'd have to think in terms of, well, it's a negative value that's getting larger. Does that count as an increase or a decrease? Which direction is that in? It's a lot easier to visualize what's going on if you just treat it as a positive value, and you accomplish that by choosing the normal vector that's already mostly in the same direction as the magnetic field. On the other hand, if your loop of wire is oriented vertically, Let's say you have a loop of wire shaped like this, and I'm going to shade in this region to represent that that's closer to the viewer. And this region is further from the viewer. In that case, you've still got magnetic field in this region of space. The loop has area. There is a magnetic field in this region of space. But we want to say this has zero flux because the magnetic field is just skimming along the surface. It's not going through the surface. So we should expect this to be no flux. And the reason for that mathematically, if we want to choose a normal vector for this, what are our options for direction of the normal vector? If we've got a loop of wire oriented like this, which directions are perpendicular to that? Yeah, to the right or to the left. And in this case, it doesn't really matter which one of those you choose. Because either way, if you choose a normal vector to the right or a normal vector to the left, either way, what's the angle between the normal vector and the magnetic field?
$90?
Yeah, this is a 90-degree angle, a right angle. So if theta is 90, that is, if the loop is oriented such that the field lines are just skimming along the surface, then the field lines are perpendicular to the normal vector. Theta is 90. And what's cosine of 90 degrees? Right, that's just going to be 0. So flux equals A times B times 0, which is 0. So that would mean no flux at all. And if you do need to choose a normal vector, if the loop is just along the magnetic field, so you're going to get no flux anyway, it doesn't really matter whether you choose left or right in this case. Where this does matter is if, let's say you're going to be rotating the loop so you do have flux. If you start off with no flux at all, so you could choose either direction for the normal vector, what I would recommend is look at what's going to happen when you rotate. Choose a normal vector that ends up agreeing with the magnetic field and then rewind to figure out which direction you have to start in. So you want to choose a direction for the normal vector such that either the starting situation has the normal vector mostly agreeing with the magnetic field, or such that the ending situation has the normal vector mostly agreeing with the magnetic field. Whichever one of those works best in the circumstances. Again, not going to affect the final result because the negatives end up canceling out, but much, much, much easier to visualize what's going on and understand conceptually if you choose a normal vector that either starts or ends mostly agreeing with the existing magnetic field. Any other questions on flux so far? So you're going to get the most flux if you have a large area loop in the presence of a strong magnetic field oriented such that the normal vector is parallel to the magnetic field. You're going to get the lowest flux if you have a small area, weak magnetic field, and an angle close to 90 degrees. And no flux at all if the angle is 90 degrees. The thing is, though, the actual amount of flux generally doesn't matter. What matters is the change in flux. And the reason for this has to do with the units of measurement. If you actually write out the units here, what is area generally measured in? Like if you wanted to describe some amount of area, what would be your units of measurement for describing that? Like if I just draw a rectangle and I say the area is 5 what?
Could it be like centimeters or meters squared or something?
As long as you've got some units of distance squared. And for simplicity, let's assume it's in square meters, because that'll work out nicely with all the other units that are in meters. So area is going to be measured in square meters. And have you seen a unit of measurement yet for magnetic field? Yeah, the unit of measurement for a magnetic field is called Teslas, written as a capital T. The usual convention there is if the unit of measurement is named after a person, the abbreviation is capitalized, but the word itself isn't. So Tesla's, no capital, is the unit of measurement for a magnetic field, abbreviated as a capital T because Tesla was a person, and a pretty cool person. Quite an inventor, an electrical wizard. But what the Tesla unit actually means, we can see this in a lot more detail, I think, if we go back to another formula where magnetic field showed up, specifically the formula for magnetic force. We want to measure magnetic field in a unit we're calling Teslas. Even if we don't know what Teslas is yet, we know the units of measurement for everything else. What's force measured in, for instance? What are the usual units of measurement for force?
Newtons.
Newtons. Also written as a capital letter because Newton was a person. And charge, what's that measured in?
Coulombs. I don't know how to say it.
Yeah, capital C, coulombs. Also a person because of the capital letter. I don't know anything about him though. And what about velocity?
Meters per second.
Right. Meters per second. Not capitalized because those are not named after people. So, and of course, sine theta is going to be unitless. Anytime you take the sine of an angle, that or cosine or tangent or whatever, those are unitless quantities. But in order for this to work, newtons has to equal coulombs times meters per second times Teslas. We could solve that for Teslas by just dividing by coulombs, multiplying by seconds, dividing by meters. So you could write Teslas as Newton seconds over Coulomb meters. So this is one way of describing the unit of the magnetic field. Magnetic field is measured in Teslas, which means Newtons times seconds over Coulombs times meters. So we could fill that in here and simplify to figure out what flux is measured in. We could simplify this a little more first though. Actually, let's go ahead and plug that in and see what we get. If we just replace Teslas with Newtons times seconds divided by coulombs times meters, can we simplify that? Is anything going to reduce there or combine? What can we cancel out? Yeah, meters is going to cancel out at least one of the meters. So meters from the numerator or denominator and one of the meters from the meters squared in the numerator. And if we combine these, we're left with a single meters times newtons. Anyone remember what newtons times meters equals? Yeah, that's joules. And you could think of that even as work. Work is force times distance. Units of force times units of distance has to equal units of work, which is joules, because work is a transfer of energy. So newtons times meters is joules. Tidying this up a little bit, we're left with joules times seconds divided by coulombs. But there's one more very convenient substitution we can make here. Anyone remember what we call joules per coulomb? Energy over charge. Yeah, this is voltage. Joules over coulombs is volts. So we're left with volts times seconds. All these units of measurement from our definition of flux just work out to volt seconds. So you can measure flux in volts times seconds. On its own, that doesn't really mean much. But this becomes very useful if we take a look at its derivative. Flux on its own, kind of meaningless. Derivative of flux with respect to time. If we're looking at not how much flux there is, but how fast the flux is changing as time passes, if you take a look at the units there, flux is measured in volts times seconds. What's time measured in? times measured in seconds, and we're dividing those. What happens when we divide? Volts seconds divided by seconds, right? Seconds cancel out. We're left with
Volts.
volts. So flux itself is kind of this weird quantity that doesn't seem to have much relation to anything else. But the rate of change in flux, the derivative of flux, how fast flux is changing, tells you a voltage. Just having flux existing isn't enough to do anything. But if the flux is changing as time passes, you get an extra voltage in the loop, almost as if there were a tiny invisible battery built into it. And as long as the flux is in the process of changing, you get this extra voltage. And what happens if you've got voltage on a wire? If you've got some length of wire and you've got a difference in voltage, what happens in a wire if you've got a high voltage on one side and a low voltage on the other side?
There's a current.
Yeah, you get current flowing, electrical current, typically equal to the voltage difference divided by the resistance, from delta V equals IR from Ohm's law. So the fact that you have a difference in voltage, usually the difference in voltage is provided by a battery or a capacitor or a generator or something like that. In this case, though, the difference in voltage isn't caused by a physical object or a chemical process. The difference in voltage is caused by the changing flux. As flux changes, it creates a voltage. But that's only while the flux is in the process of changing. As soon as you stop changing the flux, the voltage vanishes immediately and you get no more current. But you can use this to make current flow around a loop, even if there's no battery, just by changing the flux somehow. As long as you can make the change flux as time passes, you get what we call an induced voltage. Induced just meaning brought about by. So this is the extra voltage brought about by the changing flux. That voltage across some wire with resistance causes current to flow, and we call that the induced current. The current brought about by this changing magnetic flux. Any questions on that so far?
I have a question. So after after we got the joules per coulomb times second and equal to the voltage seconds, so how do we get from that to the other thing where there's like the d over dt?
The derivative of flux? That was from the fact that now that we know flux is measured in volts times seconds, if we just have volts times seconds on its own, that's not really very useful. But if we can get the seconds to cancel out, then we're left with volts. And voltage is something that can actually push current through a wire. So to change volts seconds into just volts, we need to divide by seconds. And you accomplish that by taking the flux and dividing by time. But the flux right now divided by what time the clock shows right now isn't very practical. What time the clock shows doesn't matter. But what does matter is how much time passes. And also the flux doesn't matter, but how much the flux changes during that period of time is something important. So if you look at the derivative of flux, how much the flux changes divided by how much time it takes to do so, the units work out to just volts. So this means in this case that the derivative of flux is a voltage. How fast the flux is changing tells you how much voltage you get. So for instance, if the flux is changing very quickly, you get lots of voltage and therefore lots of current. If the flux is only changing slowly, you get a little bit of voltage and a little bit of current. If the flux is constant, if the flux is not changing at all as time passes, the derivative of a constant is zero, so you get no induced voltage. There might be other voltage, like from a battery or something, but there will be no extra voltage from flux if the flux is not changing. Any other questions on that so far? So in general, flux changing causes voltage, and that what we call induced voltage. And that induced voltage can cause induced current. This leads to what we call Faraday's law, which is just a mathematical description of this concept. Faraday's law states that the induced voltage, usually written as epsilon induced, equals change in flux over change in time, the derivative of flux. And also there ends up being a negative sign in here representing direction. This negative sign basically tells you that the induced effects, the voltage and current that are created, are in a direction opposite to the direction flux is changing. So if you can establish a direction of the change in flux, an increase or a decrease in some direction, the induced effect is going to be opposite to that. For example, if we go back to the definition of flux, if flux is just area times magnetic field times cosine of the angle, what would be some ways you could change the amount of flux? How could the flux be changing as time passes?
Change the area.
Yeah, maybe you change the area. So delta flux could mean area is changing. For example, if you've got your loop of wire, maybe you squeeze the loop of wire. It could even be the same length. Maybe you're just changing the shape so it encloses less area or more area. Those changes, change in area counts as a change in flux. Or maybe you've got, another common example is maybe you've got like a sort of a couple of rails that are connected, like some of these rails just go on very long, and you've got some metal bar connecting them. If you slide that back and forth, you're getting more area enclosed or less area enclosed. So a metal bar sliding on rails, as long as there's another bar somewhere that completes the circuit, is changing the size of the loop. And so that also would count as a change in flux, which causes voltage, which causes current to flow in that loop. So you could change the area, or what else could you change? What else in this equation could be changing as time passes? Yeah, the magnetic field strength could be changing. And how could you change the magnetic field? If you've got some magnetic field in the presence of a loop, how could you change the strength of the magnetic field? Like for instance, let's say this loop of wire is experiencing a magnetic field because there's just a permanent magnet nearby. How could you change how strong the magnetic field is? Yeah, distance is going to make a big difference here. If you move the magnet further away, the wire is now experiencing a weaker magnetic field, because the further you go from the source, the weaker the effect gets. Or if you move the magnet closer, you get a stronger magnetic field. Or maybe you're holding the magnet still and you're moving the loop of wire far away, so you get a weak magnetic field. Closer and closer, you get a stronger and stronger magnetic field. So distance from the magnet might cause the magnetic field strength to change if you're moving the magnet or the loop of wire around. Also, if the magnetic field is caused by a wire, another wire with current already flowing through it. If you change the current in that other wire, you're changing the strength of the magnetic field. Maybe crank up the power to get more current in the source wire. That creates a stronger magnetic field. Increasing the magnetic field strength increases the flux. Or you make the current weaker. Making the magnetic field weaker decreases the flux. Either way, if the flux is changing as time passes, you get induced voltage in that loop. And lastly, we could also be changing the angle. Rotating to change theta. And that might mean you're rotating the loop. Maybe you've got like a bar magnet creating magnetic field and you're rotating the loop so that the angle changes. Or maybe you're holding the loop still and moving the angle, moving the magnetic or moving the bar magnet around it. That would also change the angle of the magnetic field. So either way, you could change the angle by rotating the loop or by sort of orbiting the magnet around it. Those would be changes in theta. Any of those things changing, any one or more of those things changing can change the flux. And if the flux is changing as time passes, you get induced voltage and therefore induced current. Of course, it's also possible that you're making some motion that doesn't change anything. Like let's say you've got this magnetic field pointing straight up. If you've got a loop of wire like this, you've got no flux. If you rotate it like this, you still have no flux, no flux, no flux, no flux. If the motion doesn't cause any change in the flux, then that means nothing's really happened. You get no induced voltage. But if the flux is changing, then you do get a change in voltage. Let's try an example of this. If you have let's go back to that example of just an upwards magnetic, or let's say an outwards magnetic field. I think this is going to be easier to visualize. So you've got a magnetic field pointing out of the page, or out of the board. And let's say we have let's go with that example with the metal rails. So we've got a metal rail that's very long, another metal rail that's very long, and they're connected here. And let's say we have a bar connecting those together as well. So we've got this bar here completing the circuit. This is now a loop of wire. But this bar can be sliding back and forth. So let's say we currently have the bar right here. There is some flux because we've got magnetic field, we've got a loop of wire. The magnetic field lines are going through the loop. And let's say we slide this bar to the left, making the loop smaller. First of all, we want to define a normal vector, right? If our loop is this loop here, what are our options for a normal vector? What would be vectors perpendicular to the surface enclosed inside the loop? Yeah, outwards or inwards. So our normal vector choices are outwards or inwards. We could choose either one, but it's going to be easier to visualize what happens if we choose the one in the same direction as the existing magnetic field. So I'm going to choose outwards as the normal vector. So there's the normal vector. These green arrows are the magnetic field pointing straight out. So the flux, this has flux. If we have a loop of wire, the normal vector is parallel to the magnetic field. Cosine of 0 is going to be very large. So we get lots of flux. And if we move this bar to the left, what happens to the flux?
Decreases.
Yeah, we slide the bar to the left, we get smaller and smaller and smaller area. Area getting smaller means flux is getting smaller. So moving the bar to the left causes a decrease in flux. So as the bar moves to the left, the flux decreases. And formally, flux is a scalar. It does not have a direction. But in terms of lenses or Faraday's law, we can treat the flux as having a direction in the direction of the normal vector. So if you treat the flux as being in the direction of the normal vector, so an outwards direction, but it's getting weaker and weaker and weaker and weaker. If you've got an outwards pointing vector that's getting weaker, that's a change in which direction? If you've got a vector pointing outwards, but it's getting weaker and weaker and weaker and weaker, which direction is the change? Yeah, the change is in the inwards direction. Because if you've got an outwards vector and you want to make it weaker, you've got to add an inwards vector to it. So delta flux, we can treat as being in the inwards direction. So the change in flux is inwards, but Faraday's law says that the induced voltage is opposite to the derivative of flux. So that negative sign in Faraday's law means we take the inwards change in flux and reverse that to get the actual induced effect. And here we can use the right hand rule. Take the thumb of your right hand, point it in the direction that flux is changing. Flux is changing in the inwards direction, but the negative sign in Faraday's law says reverse that. And the curl of the fingers of your right hand should tell you the direction current's going to flow. So as we slide the bar to the left, we get an induced voltage causing current to flow. In this case, we'd say that's counterclockwise. Flux is changing in the inwards direction because the normal vector is outwards, but we're decreasing it. The normal vector outwards is shrinking. So an outwards vector getting smaller is a change in the inwards direction. In the same way that, for instance, if you got an upwards vector that's getting smaller, that's a change in the downwards direction. An outwards vector getting weaker is a change in the inwards direction. So figure out which direction flux is changing, treating the normal vector as the direction of flux. Whichever direction the change is, take the opposite of that direction, use the right-hand rule, and that tells you the direction current will flow as a result of this. So we say the induced current here is counterclockwise. And you're going to get more current the faster you slide this. But as soon as you stop sliding it, as soon as the bar comes to a stop, the current immediately stops. Because the current only lasts as long as the flux is in the process of changing. No change in flux means no voltage. Any other questions on that?
I have a question about like the setup. So what is the black line that's like going through the middle?
This one? This represents just some mobile bar. So you've got these metal rails that are fixed in place, and you've got a bar that can slide back and forth on those rails. We're in the process of moving this bar to the left. As we move that bar to the left, the enclosed area gets smaller and smaller and smaller. Area getting smaller means flux is getting smaller. So flux is decreasing. Since flux is outwards, a decrease counts as the inwards direction. Any other questions on that? All right, try applying these same techniques on your own to the F&T problems on this sort of subject, and we'll look at more examples next time. See you later.